Hi there. In this video, we're going to look at hypothesis tests using the theoretical methods for proportions. Okay, so we're continuing with our learning about the central limit theorem. And with the central limit theorem, we saw that the formula for the standard error was given by the square root of pq over n. And this is for proportions specifically. Okay. So the steps for doing a hypothesis test, we're going to use the normal distribution because that's the model we get from the central limit theorem for proportions. It's similar to how we did this with a randomization distribution, but we're going to find our p-value in a slightly different way. We're going to use the normal distribution to find a theoretical p-value versus, remember, before we called it an approximate p-value because it came from a simulation. Okay. They're both really approximate because everything is approximate in statistics, but this is a theoretical versus an empirical probability. Okay, so I've got the steps right here for our hypothesis test, and I just want to review and show you the ones we did before because most of them are either the same or similar. Okay. So this was with our randomization distribution, and we'll try one both ways and see how our p-value comes out. With a randomization distribution, we wrote the hypotheses, then we simulated it and found our p-value from our simulated distribution. Then we compared our p-value with our significance level and wrote our conclusion in context. Okay, so the difference is how we get our p-value. So really only steps B and C are different. So this is steps for a hypothesis test with the normal distribution. And you might see this also written as a one proportion Z test because we're using the normal distribution. When we use the standard normal, that's the letter Z. Okay, so same step A, write the null and alternate hypotheses. Okay, B is different. So B and C are a little bit different. So I'll just underline those. For B, we're going to check the conditions to use a central limit theorem. Getting real familiar with these conditions by now. But if we don't actually have a normal model, our p-value will be meaningless, right? Because we're using the normal model to find a p-value, which is a probability. If we don't have a normal model, a normal shape, it's not going to mean, our results are not going to mean anything. Okay, so we're going to increase our chance of a type 1 or type 2 error. Okay, so then once we're sure the conditions are met, we're going to calculate what's called a test statistic. So that is new, test statistic. And that's a z-score. So I've got z equals 2. And remember, the z-score is the value minus the mean over the standard deviation. And that's why I wrote the standard error up here, because you can see it's coming from the same formula, square root of pq over n. Okay, now we set up our whole hypothesis assuming the null is true, right? So that's why I've got p0 for the null value. I'm just going to write null value next to p0. We're setting this whole thing up based on the idea that the null is true. So that's why for our mean and our standard deviation, we're going to use that null value p0. Okay, so we're going to use this, then we're going to find the p-value and put an image of our normal distribution with the p-value versus before we would put an image of our randomization simulation. Okay, then steps D and E are exactly the same. Compare the p-value with the significance level, which is alpha, determine whether your result is statistically significant, and then E, state your conclusion in context, include your p-value and whether we reject the null or fail to reject the null. Okay, so you know the whole process, but we're going to go through it with calculating this z statistic and then finding our p-value on Staplet with the normal distribution. Okay, now here's the 4 conditions I put down here because we do need to make sure that these 4 conditions are met: independence, randomization, large population, and success failure. And I just made another note there to remind you to use p0 on the success failure test because we're setting this up with the idea, and I wrote it here, assuming the null hypothesis is true. Okay, so we'll be checking conditions again, and then we're going to do another thing we've also studied, which is comparing the hypothesis test with the confidence interval. Okay, so we saw an example of this before, and just to get more practice with that, we're going to do that. We're going to do both methods with each one. Okay, that way we can see how they compare. So for each example, we'll also compute a confidence interval to see whether the conclusion would be the same or different in each case. Okay, remember they can agree and they can also disagree, but they also give us different types of information. So the significance test gives us the strength of the evidence, right? The strength, it's really the strength against the null. And the confidence interval gives us the size of the effect, because that gives us a range of plausible values. So the width of that is the size of the effect, or is related to the size of the effect. Okay, so we've had this on a previous notes, but I copied it here as well the last time we compared these two. So if the null value falls within the confidence level, that supports the null, and we would fail to reject the null. But if the null value falls outside the confidence interval, that's evidence against the null, and we reject the null. Now, if this is a one-tail test, I'm going to come back and maybe alter this a little bit, because this is for a two-tail test. For a one-tail test, we also need to see which direction it's outside, right? So I believe we're going to have an example of that, so we'll come back to that. Okay, let's go ahead and look at our first example. So let me get my next, I'm just going to pause it to get my next page ready. Okay, here I'm back, so you don't have to see my paper shuffling. First example, during the 2013 National Football League, or NFL season, the home team won 153 of 245 regular season games. Okay, so we've seen some baseball examples, now we have a football example. Test whether there is a home field advantage. So this is our claim. Is there a home field advantage at the 5% significance level? So remember, that's alpha, 0.05. And then, so I've got my steps just handy right here. But if you also want to write down, what your given information is, our p hat, that's what comes from data, right, is 153 out of 245. Might want to just see what that is. 153 out of 245 is 62.6245. 0.6245. Okay, so we'll come back and use that. Also, we have our n, right? N is the bigger one because that's the whole sample. 245. Okay, that seems like everything we're given. We might need to figure out more about what this home field advantage means. Okay, but let's go through our steps. So I'll put the A, B, C, D, E to start with. You don't have to write that, but I'll take it off eventually, but I'll write it to start. So A, write our hypotheses. Okay, so the null, and we're talking about a proportion, so we're using the letter P. The null is always P equals something, and then the alternate is going to be greater, less, or not equal to. So let's think about, what does a home field advantage mean? This is kind of like one of our random parameters that we've looked at. Well, if there was no home field advantage, let's think about it that way. If there was no home field advantage, it would be kind of 50-50, right? Whether you won your games at home and away, it wouldn't matter if you were home or away. So it would be like a 50-50 chance, okay? So our null is that there's no effect. So I'm going to say that's equal to 0.5. Okay, so you would win 50% of your games at home, half of your wins. So whether you're a good team or a bad team, that doesn't matter, but it's what you would have your half of your wins at home and half of your wins away, okay, if there's no home field advantage. If there was a home field advantage, you would win more than half of your games at home, right? So let's write this out in words, since it's this value of P0 is not given anywhere in this question. So this is winning your games at home. So win 50% of home games. Oh, sorry, it's not exactly what I meant. You're not going to win half your home games. Win 50%. Half of your wins, that's what I said before, half of your wins at home. Okay, so if you have about half your wins at home, there's no, and of course it would vary, right? It wouldn't be exactly half. It'd be like flipping a coin. Versus the alternate would be more than half, or more than 50% of wins at home on your home field. Okay, so next step is to check the conditions. Fun. Remember, I know it's kind of a pain sometimes, but this is really important. It's part of statistical thinking. Every model we use has certain conditions, and if those conditions aren't met, we could do the calculation, but it's not going to be useful, or we might end up with a wrong result because we're making a decision error because we don't really have the model we think we do. Okay, so I'm on step B right here, and I also wrote the conditions out again. This is another time, just like I was talking about with confidence intervals, you can do a quick check unless it specifies to write it out more, each one, describe each one or discuss each one. So I will do the quick version here, and again, I would probably only ask you to write each one out in detail for one problem on an assignment or quiz or test. I'm still going to do the last two have numbers, so I'm still going to do those each time, but the independence and randomization we can write out pretty quickly. Okay, so independence, I'm going to write out random sample. I do want to think about this one for a second, though. Let's think about both of these. So we're talking about our population would be all of the football games, right? When does the home team win versus, is there a home team advantage? Do teams win more than half of their games? Or half of their wins more at home? Or more than half of their wins at home? Sheesh. Okay, so I have to be careful how you state that one. Would each game be independent of each other? We're talking about all the games, there's going to be better teams and worse teams, right? So maybe not all completely independent of each other, but we're talking about like a whole season, right? So that seems like a pretty good cross-section of games. And this game over here is certainly not going to influence this game over here, right? But if one team is playing, one team is going to play two different other teams, those might not be completely independent, right? And then do we have a random sample? Well, this is interesting too, because we have 1 year where we're looking at all the games, right? There are 245 regular season games. So we're looking at all the teams, all the games, and whichever team was at home won 153 of those games, which we saw as 62%. So it's kind of like a cluster sample, right? It's like you're selecting a group and taking everyone in that group. So it's like a cluster sample. So I would just want to make sure there wasn't anything special or specific or unusual that happened in 2013. Because if there was, then this wouldn't really be a random sample, right? So ideally, this would be a random year. I'm going to write cluster sample. Okay. As long as nothing unusual, if it wasn't like Inflatorgate or Deflatorgate, whatever happened, I don't remember what year that was, but as long as it wasn't, anything unusual happening during that year, then it should be fine. Okay. Okay, then we have large population. So what we need is greater than or equal to, our sample size is 245, so I'm going to add a 0 onto that. 2,450 games. I'm going to say population needs to be greater than or equal to 2,450 games. So essentially that's like 10 of these seasons, right? That means there have to be at least 10 seasons to use one whole season. That way our population is 10 times our sample size. So yes, there have been, at least since I've been alive, and probably longer, so way more than 10. So that is good. And then our success failure. Okay, and now this one I specifically want to write out. We're always going to write this out, but I want to show you that we're going to use P0 and not P hat, right? The tempting part is to use P hat, but we're setting this whole test up with the idea that the null is true. And we did that with our randomization distribution too, right? The null, that 50%, would be right in the middle. So we're setting it up based on that. So I'm going to say n times P0, just to emphasize it, is 245 times 0.5. But again, I'm not worried about 0.5 because it's right in the middle. And n times Q0 is actually going to be exactly the same, right? Because 0.5 and 0.5 are complements of each other. So P and Q are the same. 245 times 0.5, 122.5. I would have rounded up, but they're the same, so those are both greater than or equal to 10. So we're good there. Okay, so I think we're good with, the independence is a little interesting, but we're going to continue on anyways. Okay, so we've checked our conditions. Now we can calculate our test statistic. Okay, so let's write out this value, this formula for Z, okay, for our Z score. So step C, I'll write it out with the variables first. Okay, so Z equals P hat minus P naught over the square root of P naught Q naught over N. Okay, so remember when you have that 0 in the subscript and it's not P naught, that's the P in your null hypothesis. Okay, so we do use P hat. So our Z score, our test statistic is the Z score of P hat. And this will tell us how unusual it is, okay? So let's go ahead and fill this in. So our P hat is 0.6245. Okay, so we've calculated that up above. If we hadn't calculated it yet, we would do that now. 153 out of 245. Now notice this is more than 50%. So it's 62% and a little more. So more games were won at home, but our question is that just due to chance and random variation? Or is this statistically significant? So if we have repeated samples of 245 games, how unusual would it be to get 153 if there's really no home field advantage? Okay, so remember, that's what we're asking in our hypothesis test here. Okay, so that's our P, that's our value, minus the mean, which is our P0, 0.5 or 0.50, over our standard deviation, which is 0.5 times 0.5 over N. I put the zeros in to make it consistent. Oops, instead of N, I need to put in my sample size. My sample size is 245. Okay. Okay, so let's calculate this. Let me show you how to do this on a calculator, and Desmos is also great for this as well if you like an online calculator. Okay, 0.6245 minus 0.5. Okay, so I'm going to do the subtraction on the top and hit enter. Then I'm going to divide. So again, I want to do this all in one step because I don't want any intermediate round off error. If you do this all in one step, then you need to put parentheses around the numerator here. You need to put parentheses around the subtraction so that it does the subtraction first and then divides by the square root. And I think we've talked about this with z-scores before, but it doesn't hurt to repeat it. So what I like to do is just hit enter on my calculator first. And then when I divide, it's going to take that answer and divide by the square root. 0.5 times 0.5 divided by 245. Okay, and I get 3.89. I'm going to say 3.90. Okay. Actually, let me think. I do want it, because we're going to be plugging this into Staplet, I do want 4 decimal places. 3.8975. We generally don't need z-scores to be that precise, but because we're going to be putting it in Staplet, I do want to make sure we have that. So 3.8975. Yes. Okay. And remember, that's standard deviations. That's how many standard deviations. In this case, it's positive, so above the mean. So I'm going to write standard deviations. Okay, so this is already telling us this is pretty unusual, right? So if we were to take a bunch of samples of 245, it's pretty unusual to get 153 if it's really 50-50, if this would be like coin flips. It'd be pretty unusual to get 153 heads out of 245 if it's really 50-50. Okay, so we're going to take this over to Staplet. One thing I want to ask you, is this what kind of test is this? Is it right tail, left tail, or two tail? Okay, if you said right tail, you're correct. Because it's going to the right, it's greater than, right? Okay, so let's go to our Staplet and normal distribution. Okay, and a p-value is a probability, so we're going to stick with an area. Actually, let me write down what probability we're finding first. So let me go back to the notes. D is calculate the p-value and then compare with the significance level. The oops, right today. The p-value is a probability, and because it's a right tail test, it's the probability that our z-score would be our test statistic or higher. So it's a probability that z is greater than 3.8975. And you can say greater than or equal to, because that equal sign doesn't matter mathematically. Okay, so let's go to our normal distribution. Our p-value is a probability, so we're sticking with our first operation, area under the normal curve. Z has a 0, 1, so 0 for the mean and 1 for the standard deviation. Click plot distribution, and then here's where we pick between two values, so that would be a, well actually this is where we might use outside region. We've used between before, but left would be for a left tail test, right is for a right tail test, and outside would be for a two tail test. Okay, so we have a right tail test. So I'm going to go to the right, and our value is 3.8975. That's our z-score, and I'm going to show the labels on the plot. Okay, so as I suspected, this is very unlikely to happen. They're actually saying it's approximately 0. So it's so small, they're not even giving us, it's like past 0.000000. There's maybe some digits beyond that, but it's very, very small. Okay, so I'm going to say the p-value equals 0. And then this is where we're going to either sketch or insert an image. So if you were typing this as an assignment, you would do a little screenshot or a snip of this little curve, and you can see like the z-score, that's your test score right there. That's what we put in because that's our test statistic, and that's the z-score, but we put in a z-score because it's a standard normal. So you would at least show, this area, and that you're seeing it's a right tail test. So what I'm going to do, since I'm handwriting this, is I'm just going to put a little sketch to the left here. I'm going to make a little normal curve, 0 in the middle, 1, 2, 3, 1, 2, 3 on each side. And then this is over almost to 4, right? 3.8975. And that's our p-value is actually 0. Okay, I'm not going to label this. It's a little tricky to label because it's really z-scores. So it's like test statistics. But if you were also thinking, well, to find our p-value, couldn't we just put in our mean and our standard deviation like this? Yeah, you absolutely could. So there's 2 different ways of doing it. You can use your original sampling distribution with your mean under the null, with your mean and standard deviation, and you would get this z-score in that same exact probability. So either one of those is fine, but I want you to be aware a lot of books use the test statistic, and so I want you to know that term and how to find it. Okay, and it's not always a z-score either. So sometimes we need to use a t-distribution for means, and so it's not always a z-score. That's why this one's called a 1 proportion z-test, because you don't always use the z. Okay, so that is our step D. Okay, almost. We found the p-value. I guess technically that's part of C. I'll make that part of C. But it doesn't really matter as long as you have all the steps on there. How you label them doesn't matter. So D is comparing the p-value to alpha. So our p-value is 0, which is less than 0.05. And that was our significance level that we were given, right? It says at the 5% significance level. But if it's not given, we're going to use 5% anyways. Okay, so we're definitely using 5% here. It is less than that, so that is significant, right? Remember, that means this is very unlikely to happen under the null. So this is a huge, or not huge, but strong, very strong evidence against the null, okay? So that's why we reject the null. This is significant. Or I could even, going with the strength of evidence, I could say this is very strong evidence. Okay. Very strong evidence. Okay, so now we're going to write our conclusion. That is E. And then then there's another step, right? Then we'll do our confidence interval. Okay, so this video is getting long, but I'll just keep it in the same video. Okay, so stating our conclusion in context. Okay, so the P with, I think we said it before, with a p-value of 0, or if you wanted to say approximately, it did say approximately on the app, but either way is fine. The p-value of 0, there is very strong, I'm going to say we reject the null. Reject the null hypothesis. And there is very strong evidence against the null. Okay, and now I need to put the conclusion in context, right? So remember, that's one of the disadvantages of this p-value method is it's really strong evidence against the null. But we tend to say that, you know, there's evidence that there is a home field advantage. So I could say we can conclude, or there's evidence. There is evidence of a home field advantage in the NFL. So remember, now we're not just talking about this one season, the 2013 season, because we know that more than half won, but we're inferring back to the population of all of the football games. There is is evidence of a home field advantage in the National Football League. Okay, does that match up with your understanding? Like, I think a lot of people would agree, whether it's basketball, football, anything, there is a home field advantage. Okay, so that's our whole hypothesis test. And you're used to doing a lot of this, so I think you'll be able to pick up on the new parts of it. Now we want to compare our confidence interval, okay? So I'm going to rewrite the formula for that. Remember that. So remember that's p hat plus or minus z star times the square root of p hat q hat over n, okay? So you can see we're using the same standard error formula, but the p hat that we use is different, right? We're using the null value in a hypothesis test, but we're using the observed result, the p hat, in a confidence interval, because that's all we have in a confidence interval. So we're going off of what we have. We've already checked the conditions, luckily, so we don't need to do that again. Let's go ahead and put in our numbers. So same p hat, 0.6245, plus or minus, you're welcome to try this on your own, pause it, 95% confidence, so that's the one I know, 1.96. I have to get my old notes here handy for in case we need that. P hat is 0.6245. I don't know what Q hat is, so I'm going to do 1 minus 0.6245. All over our N, which is 245 games. Okay, I'm going to write my P hat again, 0.6245. And I'm going to calculate this, clear that out, calculate this margin of error all at once. 1.96 times, or just square root right next to it, 0.6245, parentheses 1 minus 0.6245, close parentheses, divided by 245. Enter. Okay, so my margin of error is about 6%, 0.606. And that's because it's not a huge sample, right? 245. It's a lot of football games, but in terms of like a survey or something, it's not a huge sample size. Okay, so 0.0606. Okay, now we do the subtract and adding part. So I'm going to come over here to the right. 0.6245 minus 0.0606 and 0.6245 plus 0.0606. Okay, so I have 0.5639 to 0.6851. Let me write that down. 0.5639 comma 0.6851. Okay, it's fairly wide, right? Because it's a plus or minus 6, so it's around 12 percentage points wide. Okay, so now remember, let's go back to our notes on the last page and how we compare. If the null value, so we need to go back to the null value, right? If the null value falls within the confidence interval, or is the null value fall outside the confidence interval? Okay, so let's write our null value and where it would be. So our null value would be to the left, right? Because this is 56 to 68 roughly. So 0.50 would be down to the left from the interval. Okay, so it's definitely outside. So that supports rejecting the null. And this was a right tail test though. So remember, this is kind of a little more analogous to a two-tail test because you're looking at the middle 95, but we're still going to do it with this. But in that case, we need to look at the direction. So is 50%, so is just random, like there's no home field advantage, is that a plausible value in our confidence interval? No, it's not, because our whole interval is above and quite a bit above 50%. It's low, it goes down to 56. Now, we're not 100% confident that we captured the true proportion, right? But this is our 95% confidence level of plausible values, and the null is not in it, okay? And also, it is to the right of the null. So if it was, let's say if it was under 50%, but 50% was outside, then I wouldn't say, then I would say that supported the null if it was under. But it's going in the correct direction to give us evidence for the alternate, okay? So the conclusion of the confidence interval is to reject the null, same as the other one. It's to reject the null hypothesis. So the two methods agree in this case. Okay. It seemed we could restate our they both give evidence. Actually state our conclusion. Both give evidence for a home field advantage. Okay. Okay. This one is long, so I'm not going to compare the randomization distribution on this one. I'll save that for the next one when it's a little bit shorter video. Okay, I'll see you there.